Rahul here again from MySlate, and here we will continue our discussion on derivatives. Okay, now let's talk about differentiability of a function. We have already discussed this earlier, but we'll kind of do a more formal discussion and then close this topic for the day. So we have this modulus function here, three variants of that. In the first graph here on the left hand side, fx is defined at all values of x. In this middle graph, fx is not defined at x equal to 0, and in this right graph, fx is defined at x equal to 0, but it takes a different value than 0. It takes a value of 1. We have already seen that the first function is continuous and the second and the third functions are not continuous. Let us now check if they are differentiable. Okay. Now this first function we have already discussed briefly that it is not differentiable at x equal to 0 because the slope of the tangent to the curve takes different value when you approach x equal to 0 from the left hand side and when you approach x equal to 0 from the right hand side, right. So what we mean is that the limit of the derivative of f takes different value when you approach x equal to 0 from the left hand side and from the right hand side. So there is no unique derivative value. So therefore we say that it is not differentiable at x equal to 0. It is differentiable at all other points. And how about these other two graphs, other two functions? Well, they are not even continuous at x equal to 0. So there is no question of them being differentiable. So these other two functions are also not differentiable at x equal to 0, and they are differentiable at other points, just like the first one. So difference between the first and these other two functions is that the first function is continuous at x equal to 0 but not differentiable. These second and third functions, they are neither continuous nor differentiable. So you might have already guessed that continuity is a precondition to differentiability. Okay. Only when a function is continuous might it be differentiable. Okay. So these functions are not continuous because of different reasons. Here this is not defined, and here because the limit of the function from the left and right hand side is not equal to the value that the function takes at x equal to 0. But both of these are not continuous. So therefore they would not be differentiable at x equal to 0. Whereas here this function is continuous, but still it is not differentiable because it takes a sharp bend here. The derivative does not have a unique value at x equal to 0. Okay, let's try to kind of generalize this into an intuitive feel. Okay, so when would a continuous function be differentiable? So first thing, I hope you've understood that a function has to be continuous. Only then it might be differentiable. A discontinuous function would never be differentiable at the point where it is not continuous. Now, when you have a continuous function like this, where it has a smooth curve, right? In this case, whatever point you take, even the point where it is curving, right? And you try to visualize the slope of the tangent as you approach that point from the left hand side and from the right hand side, you would see that the slope approaches a common value, which is the slope of the tangent that you would draw at that particular point, right? And the same holds for various points that you can visualize on this other curve that I have shown here as well. It does have a unique slope, whether you approach it from the left hand side or from the right hand side, right? But if you look at another function which has a curve which takes a sharp bend, something like this or something like this, right? And you look at the behavior of the function at this point where it takes a sharp bend, and you look at the slope of the tangent to the curve, you will see that as you approach that point from the left hand side, you get a different slope of the tangent compared to what you get as you approach that point from the right hand side. And the same is true here. You get different slopes of the tangent when you approach this point from the left and from the right hand side. So what we say in these two cases is that there is no unique slope, and therefore at those points of sharp bends. So therefore there is no unique derivative, and therefore the derivative does not exist at these points of sharp bends, which means that these functions are not differentiable at these points. So that's what we mean by differentiability. Now look at some more examples. Here this first function is a straight line, so it is obviously continuous, and it seems that it is also differentiable. because it doesn't take a sharp bend. Any point that you take, you get a unique slope, whether you approach that point from the left hand side or from the right hand side. So it is not only continuous, but it is differentiable. The same happens here with the top middle function. You take any random point C, you approach C from the left hand side and from the right hand side, and try to visualize the slope of the tangent to the curve. You see that you will get a unique tangent, which means that f prime x, the derivative approaches a common value. The limit of the derivative exists. It has a unique value as x approaches C from the left hand side and from the right hand side. Whereas this function here, it is an example of a continuous function which is not differentiable. We have already discussed this. And what happens to these functions at the bottom? Well, they are not continuous. None of them is continuous, so there is no question of any of them being differentiable. So they are neither continuous nor differentiable. Finally, let us try to apply some mathematical rigor. Okay, we take this good old modulus function that we have seen earlier. We formally define differentiability. What do we mean when we say a function is differentiable at a particular point in its domain? Well, it should be defined at that point, and it should have a unique slope at that point, which means that f prime c should exist for it to be differentiable at c, which basically means that these two limits should be equal. And what are these two limits? These are the limits of the derivative of f with respect to x as we approach c from the right hand side and from the left hand side. So when we approach c from the right hand side, think of values on x axis slightly more than c, but very close to c. We write that as x tends to c plus. Likewise, when we approach c from the left hand side, think of values on x axis very close to c, but to the left of c, slightly less than c, and we write that as x tends to c minus. So these two limits should be equal, which amounts to same as saying that the slope of the tangents to the curve of f as we approach x equal to c from the left hand side and from the right hand side should approach the same value, should acquire the same value. Okay, and you can test here mathematically as well that the two slopes are not the same. The function, while the function is defined at x equal to 0, the slope of f prime x when we approach x equal to 0 from the left hand side is minus 1. We see that here, right? As we approach x equal to 0 from the left hand side, the slope is minus 1. Slope of the tangent to this curve is minus 1. Whereas that slope is plus 1 when we approach x from the right hand side. So this function is not differentiable even though it is continuous at x equal to 0.